welcome to the lecture number 20. We have been discussing about the rigid body dynamics. So, we will continue with that, and due course of our analysis we saw that the inertia matrix emerged, and we need to know some of the properties of the inertia matrix, because that will be helpful in discussing various problems. So, let us look into the inertia matrix. The equation that we have written, this was written as rho square I minus rho times rho tilde transpose and times d m. Okay. So, you know that if I am given a positive definite matrix, then this property x transpose A, if this is a symmetric positive definite matrix, then this must hold. Okay. This quantity will be greater than 0. Okay. So, let us say that for this V I, we use this type of notation u tilde transpose u tilde y, we write it like this. So, if we operate on this particular one, take it inside. So, if we take it inside, so this will be rho square u tilde transpose rho times rho transpose u tilde. U is an arbitrary matrix which is not depending on M. Okay. So, if we look for this quantity, this is vector u and this is vector rho tilde. So, the angle between these two, u tilde transpose rho, this we can write as u tilde magnitude times rho tilde magnitude, and say the angle between these two vectors, it happens to be gamma. So, we can write it as cos gamma. Okay. And therefore, this quantity here on the right hand side, it can be written as u tilde magnitude square times rho tilde magnitude times square times cos square gamma, okay. And this is d m on the left hand side, and this rho tilde magnitude, this is nothing but this rho. So, here we have on the left hand side u tilde transpose times I, and here one more part we are missing. So, u tilde is coming from this place. So, we need to put that also. So, we have I matrix here, identity matrix times u tilde. Okay. So, this also constitutes the this is T, this is the transpose which is on here in this place. Okay. So, I times u tilde is nothing but u tilde, and therefore, u tilde transpose times u tilde, that is equal to u tilde magnitude square. So, these two are these two terms, this term and this term, they are the same term. Okay. This is integration. So, what we see here, this is rho square, and if we write this as u tilde magnitude equal to u. So, this we can write as 1 minus cos square gamma d m, okay. And this quantity is this equal to rho square u square sin square gamma d m, and therefore, rho square rho times u sin gamma square d m, and this is always a positive quantity. So, this is going to be greater than 0 until unless sin gamma equal to 0 for all the particles of that mass. And that is a very extreme case, that is a limiting case, which will happen only if your u tilde vector, along the u tilde vector, your all masses are linearly if this is your u tilde vector. So, all masses are located along this direction itself, then only this vanishes. So, in that case the angle between these two will vanish. Okay. U tilde and u tilde and rho tilde vector, say here the we have written in terms of sin gamma. So, sin gamma means you are putting this gamma equal to 0, okay, means this vector and this vector, the rho vector. So, both are aligned, and because this vector is arbitrary, rho tilde is arbitrary, your sorry, this u tilde is your arbitrary vector, okay, you have taken on your own. Okay. So, that means the vector you have taken along that direction itself, this rho vector is lying. So, rho vector is also lying here in this direction, and this integration is over all the particles. That means that all the particles are lying over this line only. Means if I have this u tilde vector along this direction, so all your particles are concentrating over this line only. Okay. So, this is a very extreme distribution, and only for that case this will turn out to be equal to 0, otherwise it will never be 0, this will be always positive definite. Okay. So, we note down the following properties of the inertia matrix, which will be helpful due course of time. Inertia matrix, this is the real symmetric matrix. So, basically these are the what I am going to write, it is the properties of the real symmetric matrix, and because our inertia matrix also is a real symmetric matrix, and therefore, all those properties will apply. Eigenvalues of a real symmetric matrix are real, because your inertia, it cannot be complex quantity, it is a physical quantity. Okay. Can be chosen to be real, matrix can be chosen to be. So, the eigenvectors we can also choose them to be real. It is written like this, eigenvectors as one term, eigenvalues as one term. Okay, and this has significance, that if my eigenvectors are real symmetric of a real symmetric matrix can be chosen to be real, means the eigenvectors they indicate here in this case the directions. Okay. And here for this particular case they indicate the principal axis direction, as we will see later on. So, moreover, every real symmetric matrix so this has got complete set of the orthonormal eigenvectors matrix. ortho real symmetric matrix is also diagonalizable. You can diagonalize it, okay, and this is very important, because if we can diagonalize, so we can get the principal moment of inertia. For every real symmetric matrix A, there exists a real orthogonal matrix. Already we have studied about what is the orthogonal matrix. So, there exists a real orthogonal matrix M such that M transpose, I will not put this bracket, where D is a diagonal matrix. Means if we operate on this A matrix or the inertia matrix I matrix, I can convert it to a diagonal matrix, and it is a very important. Is called the M is called a modal matrix, and if its entries, if we normalize, okay, then we get the columns of the modal matrix M are the eigenvectors of A. If it is able to diagonalize A, then these are the eigenvectors of A. Okay. So, in the orthonormal form, let us say that I have this A matrix, and this operates on some vector nu, okay, and this eigenvalue problem we write it like this. Okay. So, here this nu tilde, this appears as the eigenvector, and if we normalize this eigenvector, normalize it means we convert it to a unit vector, that is convert to a unit vector, then its components they indicate, then the components this will indicate the direction cosines. Let us say that I omega we have written earlier. Okay. So, obviously, I is a matrix where you have the I 1, I 1, I 1, all these terms are there. Okay. And then you have omega 1, omega 2, omega 3. And what you are looking for, that instead of this, okay, if it can be reduced to a form where I is a scalar, okay, or instead of writing this I will write in terms of lambda, if it can be written like this. So, can we find a situation or the axis where the rotation can be represented at this is your h vector. So, the h vector or the h tilde can it be rotated represented it like this. So, this simply indicates that if your h vector, if you are writing as h 1 times E 1 cap, h 2 times E 2 cap, h 3 times E 3 cap, means in your body frame this is the E frame and this is E 1 direction, E 2 direction, E 3 direction. Okay. So, in this frame you are taking the components of the h vector, this is your h vector. Okay. So, take components along this direction. So, you can write it like this. Similarly, omega you can write as omega 1 E 1 cap, omega 2 E 2 cap plus omega 3 E 3 cap. Okay. So, in general this h and omega 1 they are not parallel. Okay. We go to the next page. Say even if we have this kind of situation I 1, I 2, I 3, and here we have omega 1, omega 2, omega 3, and this is your h, which you can write as I 1 times omega 1, I 2 times omega 2, I 3 times omega 3. And in vector notation the same thing you can write as this is the first term h 1. So, h 1 equal to I 1 times omega 1 times E 1 cap, the second term this is your h 2, this is h 2, this is h 1, this is h 3, omega 2 E 2 cap plus E 3 cap. While your omega vector we have written as E 2 cap plus omega 3 E 3 cap, but we can see that these two vectors can not be parallel because of the presence of these terms. So, even if you consider inertia matrix where the off diagonal terms are 0, in that case h and omega in general. So, we can state that in general they are not parallel. In general h is not parallel to omega. So, what can be that situation where h and omega they are parallel? Okay. So, if h and omega they are parallel means you should be able to show it like this. This is your I matrix, okay, I times omega, or writing the same term same thing like this. This is your omega vector I matrix, omega vector or omega matrix. This is a column matrix basically. So, instead of telling column matrix, I will always speak this as the vector. This is much better than speaking it as a column matrix. So, when this situation will arise that I omega will be equal to lambda times omega. So, if this situation arises, so this simply implies that we are looking for a condition where h and omega they are parallel to each other. Means if you look here in this side. So, I 1 omega 1, I 2 omega 2, so we write this term as I times omega tilde minus lambda I. Now, this is the unit matrix lambda I times omega tilde. So, if you write it this way, we can see that this is lambda times lambda I tilde lambda times this identity matrix. So, this is indicating basically your eigenvalue problem. So, rotation, if the rotation happens along a particular principal axis, only then this situation will be satisfied, or as earlier we have discussed that or let us say that this is my the first axis, second axis and the third axis, and this is the principal axis. first principal axis, second principal axis, and this is the third principal axis. So, this kind of notation we can have only in the case where rotation itself is along one of the principal axis, otherwise we cannot get this. Okay. So, if we write it in this way, so let us say that you have A is equal to lambda x, and then you are writing this as lambda, and this is the identity matrix lambda x equal to 0, and then you are solving it. Okay. So, the same thing, this is the eigenvalue problem. So, here also this is the eigenvalue problem. So, if you try to solve this problem, so in that case for the non trivial solution, we look for the non trivial solution, means omega tilde this is not 0, it is not a 0 vector. So, we will particularly explore this expression. So, what we see that for our problem to be traceable, this must be singular. Okay. So, for non trivial solution, determinant of this must vanish. This implies that this must be singular, only then the determinant will vanish. Okay. And then this lambda I tilde, if you set it to 0, so you can solve for lambda. So, you get 3 values for lambda, say this is lambda 1, lambda 2, lambda 3, okay. And these 3 values they will indicate the 3 principal moments of inertia. So, the 3 principal moments of inertia. It can happen that all of them like they are lambda, 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 all of them are same. Okay. That happens in the case of the sphere, where all the moment of inertia along all the perpendicular direction, all the 3 perpendicular direction, whichever you choose, it happens to be the same. Okay. Now, here this omega tilde which is appearing, this is your eigenvector. Okay. So, for each of the eigenvalue you can solve for this eigenvector, and then this eigenvector, this indicates the direction of the principal or the principal moment direction. So, we have the lambda 1, lambda 2, lambda 3. So, taking this lambda 1 we can solve this. So, one value we will have to assume, the rest other 2 we can solve for, and if it is repeating. So, you have to apply the process for solving eigenvector, getting eigenvectors for the repeated eigenvalues, and you can look for that technique in the book the Kreyszig, Engineering Mathematics by Kreyszig. Okay. So, this omega then corresponding to this lambda 1 what you get, corresponding to this lambda 1 the omega tilde that you get, this gives you the eigenvector which locates the first principal moment of inertia direction. Okay. Similarly, from lambda 2 you will get omega tilde. So, for this omega tilde, now omega tilde as a whole if you look, it may not be a unit vector. If it is not a unit vector, just normalize it. Okay. So, each component of this omega tilde then omega tilde, the next one, let us say for I will write it in the exponent terms, not to indicate these are the components of omega, but rather these are the eigenvectors themselves. Okay. Similarly, for lambda 3 is omega tilde 3. So, the components of this omega tilde, they will be cos alpha, cos beta and cos gamma. These are the direction cosines, and cos alpha times cos beta square times cos gamma square, as we have discussed in our rotation, cos alpha square alpha plus cos square beta plus cos square gamma, this will be equal to 1. Once you have normalized it, so the normalized omega tilde, which is the eigenvector here in this case, it will indicate the direction cosines of the principal direction. So, let us get into this through a figure. Say I know the mass distribution with respect to this axis E 1, E 2, E 3, where we have all I 1, I 1 2, I 1 3, I 2 1, I 2 2, I 2 3 and I 3 1, I 3 2 and I 3 3. All of them are available to us. Okay. Thereafter, by doing this operation, this solving for the eigen values, we get to this point. Okay. That is, we solve for eigen values and the eigen vectors. So, if this is my omega 1, so omega 1 will have components, I can indicate it by say omega alpha 1, beta 1, gamma 1. Similarly, for this we can write here as alpha 2, beta 2, gamma 2. So, these eigen vectors. So, now I have the principal direction, let us say this is the first principal direction, and I will indicate this as E 1 maybe prime. Okay. So, if I indicate by E 1 prime, so the angle from here, this will be your alpha 1, this angle will be beta 1 and this angle will be gamma 1, and then the cos alpha 1, cos beta 1 and cos gamma 1, this is your corresponding eigenvector here, okay, normalized eigenvector. So, this normalized eigenvector, it locates the orientation of the, or it is just about the orientation of your principal axis direction. Okay. Similarly, you have the second direction, let us say it is along this one. So, this is your E 2 prime. So, the same way the angle from here to here, this will be alpha 2, from this place to this place this will be beta 2, and from here to here this will be beta 3. And in the same way, then you can take the third direction, which is E 3 prime. So, E 3 prime, you take the angle from this place to this place, this will be your gamma 3, from here to here this angle will be your alpha 3, okay. And from this axis the angle will be, I cannot show it here now, this will be beta 3. So, this way all your principal axis direction, principal moment of inertia axis direction, they get located. Okay. So, if I write here I 1, I 2 and I 3 as the principal moment of inertia, then this indicates that you are taking along this axis I 1 about this axis, I 2 about this axis and I 3 about this axis. And the mass distribution with respect to this new axis I 1 E 1 prime, E 2 prime and E 3 prime, it is such that all the off diagonal terms I 1 2, I 2 1, I 3 1, I 1 3, I 2 3 and I 3 1, these are all equal to 0. Okay, they vanish. So, mass distribution then with respect to this axis, it becomes such that those terms are vanishing. And this is quite often done, that once say you have a satellite and you want to get its moment of inertia. So, first you will you have a big satellite. Okay. So, there are different components inside. So, you will calculate, there are software available, or either you can do it yourself, each component you have certain mass. So, you first choose certain point and from that point then you can calculate the moment moment of inertia of the each of the component. So, this using the parallel access theorem, you can calculate the moment of inertia of each of the component, and you can build the moment of inertia for the whole system. And once you have got the moment of inertia for the whole system, which is looking like this. So, in that case, thereafter you can reduce it to the format by considering the eigenvalue problem, and you can get here lambda 1, lambda 2, lambda 3, and also the principal axis direction. And once you get the principal axis direction, so you can work with then I 1, I 2, I 3 instead of working with this whole matrix, because this is very easy to handle in controls rather than handling this particular part. Okay, so, this is about the moment of inertia consideration, and a lot more can be discussed, but we have limited number of lectures, only 30 lectures for this particular course, and already we have covered around 10 lectures. That lecture number 20, it is a half of an hour. So, total 10 hours we have covered. So, rest 20 hours we are having in hand to cover the dynamics part. So, I will not go in details of this moment of inertia, rather you look into the engineering mechanics book by Erwin Sims or either by Beer Johnstone. In both the books, it is given in great details. So, after reading this, you will be able to solve certain problems. So, this particular course I am concentrating on the dynamics and controls of the satellite. I will discuss more in more details the dynamics and to some extent the controls, because dynamics itself it takes a lot of time. So, we continue in the next lecture. Thank you very much.